Good morning. This is my DL assignment submitted to Kannadasan sir, and this is submitted by Rahul Mantri. We'll be doing 9 questions today related to the digital logic subject. The first question is to explain about the Huntington's postulates or the common postulates. In 1854, George Boole introduced a systematic treatment of logic and developed for the purpose of an algebraic system now called the Boolean algebra. In 1938, C. Shannon introduced a two-valued Boolean algebra called the switching algebra, in which they demonstrated that the properties of the bistable electrical switching circuits can be represented by this algebra. For the formal definition of Boolean algebra, we shall employ the postulates given by E.V. Huntington's in 1904. So these, as you can see, are the basic preliminary building stage of the Boolean algebra. Now, what the Huntington's postulate states is the Huntington postulate states that closure with respect to the operator plus and closure to the respect to the operator dot products. And the identity element also says that 0 plus x is equal to x plus 0, and both of them will be simultaneously equal to x. 1 into x and x into 1 is also equal to x. So goes the commutative property and the distributive properties. And also, if there is an element x belonging to B, then there exists an element x dash belonging to B called the component of the x. Also, x plus x dash will be equal to 1 and x into x dash will be equal to 0. So these are the six Huntington's postulates. Now, as to the second question. Our second question tells us to compare between a 4-bit number. The 4-bit number will be provided as an input to the user to the machine as two numbers of 16 bit each. Now these numbers can be further divided into three categories depending on the magnitude. They can be A equal to B, A is less than B, and A is greater than B. So what we do here is we draw a diagram based on the equations for the magnitude comparator numbers. Now, as you can see here, yes, A3 and the inputs here are A, B, C, D, A and B. A and B will be provided as to 16-bit, so 2 to the power 4, so 4 inputs for both A and B. Now, after going in the starting, we've provided a XOR gate mechanism. There's an NOT gate and then there's AND gates. So this gives us a XOR gate output for both all of them. And after that, we take this into a XOR, not a XOR gate, a NOR gate. Then the NOR gate gives us x3, x2, x1 and x0. These values can be provided to give a equals to b. After that, for giving the value for a is less than b or a is greater than b, we from this equation put the logic in the logic diagram. We make this Boolean expression, and so we derive with the 4-bit magnitude comparator. Now, question number 3. Now, question number 3 tells us to prove that for a three variable Karnaugh map, if you draw, then the expression for m0 plus m1 plus m3 plus m4 plus m5 plus m7 should be equal to the maximum expression of m2 plus m5. Now, if we draw the Karnaugh map, as you can see, we derive with a logical Boolean expression, and so for the SOP and POS, both of them. Now let's consider that this is one is F1 and one is F2. So after that, if you want, you can draw a truth table considering a three variable input, deriving to an output, and the output is given here, which as you can see is equal for both of them, which proves that this uh, expression is equivalent. Question number 4. Question number 4 tells us to plot a Boolean expression in the Karnaugh map. Given the Boolean expression y is equal to ABC dash plus ABC plus ABC dash. Now, how we do this is, now we consider this. Yes, I hope you can see. Yeah, we consider this A to be 1 and this A, B to be consider 1 and this to consider 0, so that we get a value of 5. So now we plot 5 into the Boolean expression. Okay, so as I was going, A, B, C dash means 1, 1, 0, which means 6. So you plot 6 in the Boolean expression. A, B, C, which means 7. So you plot 7 in the Boolean expression. A dash, B, C dash, which means 2. So you plot 2 in the Boolean expression. After this, you can further simplify this into another Boolean expression, and you can draw a logical circuit diagram for that. Another such question given to us is a max term question, question number 5, which is y equal to, and that's the max term expression. This is a four variable this will be a four variable Karnaugh map. As you can see, there are four variables A, B, C and D. So now, as we know, in a max term question, A is not equal to 1, but A is rather here equal to 0. So this will be considered as 0, 0, 1, 0, 1, which will be 1. So you put 1 in the Karnaugh map. And further, you simplify these values to be 1, 3, 6, 13 and 14, and you place those values on the Karnaugh map. So these were the first 5 questions that we just did. Now we'll be moving on to the next set of questions. Okay, question number 6 is again similar to a question we have done before, as this is a 2-bit magnitude comparator, which is nothing but instead of the four different inputs that we were giving in the 4-bit magnitude comparator, here the numbers won't be A0, A1, A2, A3, but rather A0 and A1. And there won't be any A2 and A3 because this is just a 2-variable input. So now, explaining the diagram of the 2-bit input comparator. As you can see, sorry, for A equals to B, here also you have to give the input as x0 and x1. The both using a XOR gate. Then then A is less than B and A is greater than B. We are using all basic NOT and NOR gates and XOR gates to derive to these expressions. Question number 7. Now this is a very interesting question. This is a JK flip-flop question. Now the question, in the question we've been given this cycle. Now this cycle tells us where the state at as of now, what's the present state, what is the next state, and then what is the state after that, and where does it come back to. So from that we can get a state table from the truth table. Truth table gives us that for a value 0 0, what would J and K flip flop give. So in this, so when you go to the present state, if you look at A, what you have to see is the first digit and the preceding digit, and then both of them you have to compare as A and B, and then place the output 0 and X into the state table. Similarly, if you do for every one of these, then you will get a K map which you can simplify for the 4 variable input, and from the K map you will get an expression for every of the solutions. Now, after you get the logical expression for every of the from every Karnaugh map, you'll have to draw 8 Karnaugh maps, as JK flip-flop for 4 input variables will give you 8 Karnaugh maps. So you draw Karnaugh maps for both A, J, K, and then BJK, CJK, and then DJK. Here you can see is the circuit diagram for the JK flip-flop. JK flip-flop doesn't have a clock and has J and K instead. It's different from a D flip-flop or a T flip-flop, as it doesn't have a synchronous clock. So now as to how you end up with the circuit, yes. So let's see. Let's assume we are solving for these three. Now BK, A dash D. Now we're getting A dash from here. Let's take D from here. Then we get A dash D here. We take it back. We give it to BK since this was BK. Similarly for DJ, it's A dash B dash, and for DK, it's A dash B dash C dash plus A B dash C dash D. So as you can see here, for DK, we've taken both the inputs A dash B dash C plus A B dash A dash B C dash D, and we've given an OR gate to add both of these and then give it to the DK. Now jumping on to the 8th question. Now these are theory questions, 8th and 9th questions. What the question says is differentiate between synchronous counter and asynchronous counter. So in a synchronous counter, output changes at discrete intervals of time in a circuit based on an equal state or state time defined by external means such as a clock. Example, flip-flop, synchronous counters. Asynchronous counter, output can be changed at any instant of time by changing the input. It is a circuit whose state time depends solely upon the interval logic circuit delays. It doesn't depend, it is not preliminarily given by the user, but rather it depends on the circuit delays. Example, asynchronous counters. Now, the question number 9 asks us to define modulo n counter. What a modulo n counter is it is a counter that goes through a repeated sequence of n counts. For example, a 4-bit counter in a mod 16 counter, a BCD counter and a mod 10 counter. So what a modulo n counter is like a for loop for your digital logic circuits. It goes in a counter n number of times. So these were the 9 questions provided to us. This is Rahul Mantri. Thank you for watching the video.